A mysterious visitor from another star has entered our solar system. Its name is 3I Atlas, only the third confirmed interstellar object ever discovered. It's fast, it's unusual, and it's revealing secrets about worlds far beyond our own. But the big question remains, is it heading toward Earth or just passing through? Let's break it down and see what NASA and astronomers are saying about this cosmic intruder. Imagine waking up to find a new return address stamped on the sky from elsewhere. That's what astronomers felt when the Atlas telescope in Rio Hurtado, Chile, flagged a fast-moving blur on July 1st, 2025. The system was built to warn us about asteroids that might one day cross Earth's path, but this object wasn't local. Follow-up calculations showed a path that doesn't loop around the Sun. It slashes through and keeps going. That's the signature of an interstellar visitor. Within days, the Minor Planet Center confirmed it with a historic name, 3I Atlas, the third interstellar object ever seen after 1I/Oumuamua 2017 and 2I/Borisov 2019. At first, observers weren't even sure what it was. Some images showed a star-like point, no fuzzy halo, almost asteroid-like. Others hinted at a tiny smudge, maybe the start of a coma. As more telescopes came online across both hemispheres, the picture sharpened. There was indeed a faint envelope of dust and gas. That pushed the consensus toward comet, and the object received a second label you'll see in papers, C/2025 N1 Atlas. The reason it all felt urgent isn't just the rarity. An interstellar orbit is hyperbolic, eccentricity greater than 1, so every exposure counts before the object fades back into deep space. Hubble then stepped in to set some size guardrails. Even with its sharp vision, Hubble couldn't resolve the solid nucleus directly, but its image and brightness constraints put the nucleus somewhere between a few hundred meters and a few kilometers across, with an upper limit around 5.6 kilometers. That range is big enough to matter for chemistry, yet small enough that sunlight can quickly change what we see from the surface. In practical terms, it's large for a rock, modest for a comet, and perfect for science. Speed told the second half of the story. 3I Atlas is barreling through the inner solar system at roughly 130,000 miles per hour, about 210,000 kilometers per hour. That's far above the escape speed near the Sun, which is exactly what you expect from a drifter not bound to our star. When ESA's ExoMars Trace Gas Orbiter grabbed the closest look from Mars's neighbourhood, in early October 2025, the images showed a dim, fast dot against streaked starfields, proof of just how quickly this thing is booking it past our planetary lane. Then came the chemical plot twist. Using JWST's near-infrared spectrograph, researchers measured the gases flowing off the nucleus and found a coma rich in carbon dioxide, with a CO2 to H2O ratio around 8:1, among the highest ever seen in any comet. That's not a small quirk. It hints that 3I Atlas formed in a very different nursery than the comets we know, perhaps near the CO2 ice line of its birth system, or in a radiation-soaked environment that altered its surface over eons. Add detections of H2O, CO, OCS, and even water ice signatures, and you get a cocktail that's familiar in ingredients but wildly skewed in proportions. As if that weren't enough, NASA's Swift Observatory picked up hydroxyl, OH, the ultraviolet fingerprint of water, when the comet was nearly 3 astronomical units from the Sun, a distance where most homegrown comets are still quiet. Seeing water activity that far out is weird. It suggests either unusual internal plumbing, volatile pockets venting early, or a surface and subsurface layered in ways we haven't modelled well for interstellar bodies. The upshot, 3I Atlas is forcing scientists to update the rulebook on what turns on a comet. Origin stories matter with visitors like this, and trajectory forensics point to deep time. By integrating its motion backward and checking for close stellar encounters, researchers found no obvious recent nudge from nearby suns. That hints at a launch long ago, possibly from the outer frontier of the early Milky Way. the boundary where our galaxy's younger thin disk meets the ancient metal-poor thick disk. If that's right, 3i Atlas could be older than the Sun by billions of years, a preserved shard from a planetary system that formed when the galaxy itself was young. It's not proof of age, but it's a compelling lead, and the kind of clue we only get from objects that don't belong here. Meanwhile, the third visitor label is useful for more than trivia. Oumuamua looked nothing like a classic comet. No visible coma, odd non-gravitational acceleration, and a shape and spin that still spark debates. Borisov, by contrast, behaved like a textbook comet, with an obvious tail and chemistry not too far off the norm. 3i Atlas sits between those extremes, unambiguously cometary, yet chemically exotic and active at distances that defy expectations. With just 3 examples, we've already sampled a surprising diversity of recipes for small bodies from other suns. That's a strong hint that planetary systems across the galaxy cook up comets in many ways with different mixes and temperature histories, and for anyone wondering about danger, being interstellar doesn't make it risky. If anything, the opposite. The same hyperbolic orbit that brought 3i Atlas to us guarantees it doesn't stick around or loop back for a later rendezvous. Official trackers place its closest Earth distance at about 1.8 astronomical units, roughly 270 million kilometers, comfortably beyond any hazardous zone. As a story hook, from another star is dramatic. As a trajectory, it's a clean flyby. So when we say third visitor from the stars, we're not just counting souvenirs. We're opening a tiny door into other solar systems' pasts. A Chilean survey designed to watch our backyard spotted it. A global network proved it's not from here. Space telescopes dissected its chemistry and found something we hadn't seen before. And now, for a few brief months, we get to learn how worlds form under alien skies, by studying the dust of one that left home long, long ago. If you've seen headlines or scary thumbnails asking whether this cosmic visitor is coming at us, here's the simple truth. 3i Atlas is not on a collision path with Earth. Its route through the inner solar system keeps it comfortably distant the entire time. Even at the moment when it's closest to Earth, it stays roughly 1 3/4 times farther away than the distance from Earth to the Sun, on the order of hundreds of millions of kilometers. In plain words, a very wide miss. A helpful way to picture it is to imagine Earth and this comet on different highway levels. From some camera angles, the lanes look like they cross, but there's an overpass between them. During Earth's closest approach timeframe, 3i Atlas is actually on the far side of the Sun from us, tucked safely behind our star from our viewpoint. That geometry alone rules out any possibility of a surprise last-minute turn into our lane. You might also hear that it's heading straight toward the Sun, which can sound dramatic. Yes, it dives inward, but it never plunges deep into the Sun's neighbourhood. It grazes the inner system and makes its tightest turn around the end of October, just inside Mars's orbit, and then departs forever on a one-and-done swing. This is exactly what astronomers expect from an interstellar interloper. No looping return, no second chance to get close to Earth. On its way inward, the comet gave Mars the closest audience, tens of millions of kilometers, while spacecraft there tried for measurements. That closest look wasn't because it was dangerous. It was because Mars happened to be well placed for observations as the visitors zipped by. From our standpoint on Earth, the comet never enjoys a similar rendezvous. Why are scientists so confident about all this? Because the orbit has been pinned down by hundreds of observations from multiple observatories, then cross-checked by independent teams. With every new night of data, the uncertainty in its path shrank. The result is a well-constrained hyperbolic trajectory, the hallmark of a body that isn't bound to the Sun. Once that became clear, the official designation followed and the "is it a threat" box was closed. Numbers can be reassuring, but the timeline helps too. After it hooks around the Sun in late October, it disappears in the glare for a few weeks, and then reappears on the other side in early December for another observing window, still far from us, still outbound, still no hazard. From there it heads for the outer solar system and fades from even our best telescopes. What about the speed? 3i Atlas is among the fastest sky travellers ever clocked here, which makes for exciting headlines. Fast doesn't mean dangerous though. Speed simply confirms its deep space origin. Think of it as a tourist on an express train that never stops at our station. Its momentum carries it through, past the sun, and back into the dark between the stars without ever sharing our track. Finally, a word on why official voices keep repeating no threat. Planetary defense teams at space agencies exist to model worst-case scenarios. If there were any credible way to twist the trajectory into a problem for Earth, you'd hear it from them first, not from rumour mills. Their verdict is straightforward: safe miss distance. Other side of the sun at our nearest moment, no impact risk. That's the bottom line, and it's based on precise tracking rather than vibes. So yes, 3i Atlas is coming through the inner solar system, and that's thrilling for science. But coming to Earth? Not even close. Think of this part as the travel itinerary, the where and when of a visitor who refuses to slow down. 3i Atlas cuts into the inner solar system on a steep, unbound path, skimming the inside edge of Mars's orbit before it swings around the sun and vanishes back into the dark. The important piece of geometry is that Earth spends this entire drama on the other side of the stage. Even when the comet is closest to our world, it's still far away, and during the most exciting moments near the sun, we're separated from it by our star itself. Right now, the comet has already brushed past Mars's neighbourhood, giving orbiters there the best vantage point anyone will get. That's not a warning sign, it's simply a lucky lineup for science. From our vantage, the comet's inward approach keeps it buried low in the sunrise or sunset glare, never rising to the kind of height or brightness that casual stargazers would notice. This is the essence of the flight plan. Great for instruments, frustrating for eyeballs. The turning point of the journey comes at the end of October, when 3i Atlas reaches its tightest swing around the sun. It doesn't dive deep. It clips just inside Mars's orbit, whips around, and heads back out. That bend happens while Earth is almost exactly opposite in the sky, so ground observers on our planet lose the comet in the sun's glare for a few weeks. You can imagine it like watching a plane fly behind a mountain. There's a moment when you know it's making a sharp turn, but you can't see the manoeuvre until it emerges on the other side. After this blind spot, the comet reappears on the far side of the sun from Earth. That return to view happens in the early part of December, when it emerges into the dawn sky, low and faint. The morning window will be the first chance for many observatories to resume tracking its dust and gas as it cools and fades. If you're following along as a sky watcher, this is the phase when patient, well-equipped observers in dark locations can attempt it with larger telescopes and sensitive cameras. For the rest of us, this will remain a science target, rather than a naked-eye spectacle. The outbound leg also sets up a string of safe, distant planetary flybys that help define the path. The comet has already slipped by Mars at a comfortable distance. Not long after it swings around the sun, it glides past the general orbital region of Venus. Again, not close, just a clean pass by the inside lane. From there, the itinerary stretches outward. By mid-December, Earth gets its formal closest approach, which is still very far and on the opposite side of the sun from that October turn. Then, months later, in early spring, the comet makes its best approach to Jupiter's realm as it speeds toward the edge of the solar system, fainter every week. From a storytelling point of view, the most striking thing about this schedule is how it foils our instincts. We're used to comets that swing near the sun and put on a show for Earth soon after. 3i Atlas refuses to play that script. The angles never give us a dramatic high-in-the-sky appearance. Instead, the action is distributed across many instruments in many places, spacecraft catching quick snapshots from Mars at the start of October, solar-facing telescopes watching the dust and gas flare as it rounds the sun at the end of October, and then ground-based observatories picking up the thread again in December as the comet drifts into the dawn. Scientifically, that sequencing is gold. The Mars side pass gives before data points on how the coma behaves far from the Sun. The perihelion turn, our word for the moment of closest pass to the Sun, offers during measurements when the heat is strongest and the comet's chemistry is roaring. The December reappearance provides the after phase, which lets researchers watch how quickly the coma collapses and which gases linger as the comet cools. Stack those phases together and you get a rare 3-act play. Wake up, peak, wind down. There's also a visual twist that observers will chase across these phases. Because a comet's tail always points away from the Sun, the tail we see from Earth can change shape and apparent direction as our viewing angle shifts. Around the time the comet is nearly behind the Sun from our viewpoint, the geometry may briefly make dust along the comet's orbit appear as a stubby spike pointing toward the Sun, a perspective effect sometimes called an anti-tail. Whether 3i Atlas shows this cleanly depends on how much dust it releases and how the line of sight stacks up, but the weeks bracketing the end of October and the resumption of observations in early December are prime time to look for subtle changes in the tail structure. For anyone trying to plan backyard observations, here's the honest guidance. Expect a challenge. The comet is a telescopic target throughout, never a headline-grabbing spectacle for the unaided eye. The best window for amateurs arrives after it reappears in December's pre-dawn sky, low on the horizon, where a larger telescope and a dark sight might tease out a faint fuzz and, if you're lucky, a short tail. Photographers with tracking mounts and long exposures will do better, but the visuals will still be subdued compared with bright comets of the past. The reward is less about a dazzling view, and more about the thrill of capturing a visitor from another star in your own images. By early 2026, the story winds down. 3i Atlas will have slipped past Jupiter's neighbourhood and be heading for the outer darkness, its activity dwindling as sunlight weakens. The path never turns back. There's no encore, no return engagement decades later. This is a one-time pass. In through the door by Mars, a fast pirouette around the Sun, a quiet exit across the tiles of the outer planets, and out into interstellar space again. If the earlier chapters asked whether it's coming to Earth, this chapter answers with a map. It's cutting through our house, yes, but along the far corridor, out of reach, tiptoeing past the rooms where we live, and gone before most of us have even drawn the curtains. Start with the simplest surprise. What 3i Atlas breathes out is not what most comets around here breathe out. In our backyard, when sunlight wakes a typical comet, water vapour tends to dominate the coma, with carbon dioxide and carbon monoxide as important but usually secondary players. 3i Atlas flipped that script. Early infrared spectra showed a coma in which carbon dioxide vastly outweighs water, by a margin so large that veteran comet scientists did a double take. That one ratio alone hints at a life story written under alien conditions. Colder birthplaces, different chemistry in the nursery disk around its long-lost star, or surface layers processed by ages of radiation to leave carbon-rich ices nearer the skin. However you slice it, this mix is not business as usual. The second oddity arrived from a completely different slice of the spectrum. Before the comet had drawn very close to the Sun, an ultraviolet signature of water showed up anyway. You can imagine how that scrambles expectations. At distances where many local comets are still hitting the snooze button, 3i Atlas was already venting water products into space. One way to make sense of this is that sunlight was lofting fine grains of water ice off the surface, tiny reflective snowflakes that then sublimated in the coma, so the water engine can switch on earlier than usual. Another possibility is that carbon dioxide and carbon monoxide, which wake at colder temperatures than water, opened cracks and pathways that let deeper reservoirs start to breathe. Either way, the comet breaks the usual timeline for when water reveals itself. Even its look is a little strange. High-resolution images suggest a compact asymmetric coma rather than a dramatic sweeping tail in early views. That can mean big dust grains that don't get pushed far by sunlight, or jets that favour one side of the nucleus, behaviours tied to how the surface is patched together. If you picture the nucleus as a dark, lumpy snowball with patches of different ices and crusts, then a single sunny region can behave like a rotating sprinkler. As the nucleus turns, that jet paints a slightly off-center teardrop glow. Later, as viewing angles shift around perihelion and into the outbound leg, observers will be watching for shape-shifting structures, a brighter sunward spike, a longer, thinner dust fan, or a narrow gas tail peeling away from the dust. Subtle, yes, but those shapes are fingerprints of grain-size spin and the plumbing of vents under the surface. The size story is also odd in a quietly helpful way. Hubble's sharp eyes couldn't carve the nucleus out of the haze, but they boxed it in. Not a giant iceberg, not a pebble either. Likely somewhere between a few hundred meters and a few kilometers across, with an upper limit around 5.5 kilometers. That middleweight size matters because it's large enough to preserve layered history, but small enough for sunlight to rapidly transform the outer skin. In practice, that means we can watch the surface evolve within weeks. Crusts crack, fresh ice is exposed, chemistry shifts, and the coma's recipe changes in real time as heat soaks in. Few objects give us such a fast-moving lab. Speed is another part of the weirdness package, not because speed itself is rare for interstellar visitors, of course they're fast, but because 3i Atlas is sprinting at the high end even by those standards. That blistering pace helps explain why the coma woke so early. When you're racing inward, the temperature curve steepens day by day, and the volatile's first sequence plays out like a time-lapse. Carbon dioxide jets can dominate before water normally would, shaping the coma in ways Earth-based observers don't often get to see. It also means subtle changes happen quickly. A week of data here is like months of evolution for a slow, distant comet. Put all of these quirks together and you get a picture that doesn't neatly match either of our previous interstellar guests. Oumuamua had no obvious coma, and left us arguing about what propelled it. Borisov behaved like a classic dusty comet from day one. 3i Atlas splits the difference in the most instructive way. Unambiguously cometary, but with a chemistry dialed to carbon dioxide, and a schedule that brings water on stage earlier than expected. That diversity across just 3 examples is a loud signal that planetary systems make small bodies with wildly different recipes. It's like tasting 3 breads from 3 kitchens and finding one is unleavened, one is sweet, and one is spiced. You immediately know the bakers were working from different cupboards. For researchers, this is a once-only chance to watch a carbon dioxide-driven comet in close-up. Infrared observatories chase the gas mix and temperatures. Ultraviolet instruments key in on the water fingerprint and how it waxes and wanes. Polarimetry specialists use scattered light to deduce grain sizes and textures, while spectroscopists go hunting for faint signatures of rarer molecules, sulfur-bearing species, organics with delicate bonds and other traces that tell you how the ingredients were cooked or frozen before the comet ever left home. Each method is a different stethoscope pressed to the same patient, and the combination is what makes the diagnosis robust. And then there's the deeper mystery. Why carbon dioxide? 3 broad stories are on the table. One says 3i Atlas formed beyond a cold boundary in its natal disk, where carbon dioxide frost was abundant and water stayed locked deeper down, so today's sunlight merely resurfaces that heritage. A second says eons of space weathering, cosmic rays, micrometeoroid sandblasting, hardened a sun-baked crust that traps water more effectively than carbon dioxide, so the easier-to-escape gas wins the early race. A third blends both. Regions of the nucleus with different histories wake at different times, and we're catching the carbon-rich districts first. Over the weeks around perihelion and into the outbound phase, watch for that ratio to evolve. If water surges and the balance equalizes, layering is likely. If carbon dioxide keeps running the show, formation environment jumps higher on the suspect list. However it unfolds, the comet is generous with teachable oddities. It challenges our assumptions about where and how comets store their ices, forces new models for early activity far from the sun, and offers a laboratory to watch carbon-driven jets sculpt a coma almost in real time. Most of all, it widens the space of possibilities. We didn't just find another interstellar visitor, we found one that insists on being itself, carbon-loud, early waking, fast-changing, and in being itself it's telling us that the galaxy's kitchens stock their shelves in ways our own pantry never prepared us for. If you want to imagine where 3i Atlas began, picture a young star wrapped in a wide cold disk of dust and gas, a messy nursery where pebbles stick, boulders collide, and icy worlds take shape far from the warmth of their sun. In that outer country, sunlight is weak, and time moves slowly. Grains gather into clumps into mountain-sized bodies, and some of those bodies end up on unstable orbits that graze the realms of growing giant planets. That's where the drama starts. A newborn Jupiter-like world doesn't just sit quietly, it kicks. One close pass and an object can be flung into a wildly stretched path. Another pass and it's hurled clean out of the system, tossed into the dark like a stone skipping off a lake. Billions of years later, one such exile turns up in our sky, and we give it a name, 3i Atlas. There are many ways to make a castaway. In some systems, giant planets migrate inward or outward as they exchange momentum with the disk, sweeping up debris as they go. Anything caught in their gravitational weight can be scattered to the outskirts or ejected entirely. In other systems, two or more giant planets pull a smaller body back and forth like a tug of war until one final encounter sends it packing. Binary stars can amplify the chaos. A second sun passing close every few decades or centuries can jostle comets out of the star's deep freezer and straight into the slingshot lane. Even long after a system settles down, a passing star can brush the outermost reservoir, an Oort cloud-like halo, and shake loose a shower of comets. Some fall inward, some head for interstellar space, and a few will wander the galaxy for eons. Once an object is evicted, the galaxy itself takes over as the landscape. Interstellar space isn't empty, it has tides and weather of its own. The slow pull of the Milky Way subtly reshapes orbits. Giant molecular clouds, vast curtains of gas and dust, can nudge a traveller's path by small amounts that add up over millions of years. Cosmic rays and micrometeoroid dust storms sandblast the surface, changing the outer millimeters into a hardened rind. That rind may trap some ices while letting others seep out more easily, creating a layered skin that remembers every era it has survived. If you could slice the nucleus like a cake, you might see the story written in alternating bands, a crust annealed by radiation, a pocket of ancient frosts, a vein where volatile gases once vented, and deeper down the untouched chemistry of its birthplace. What kind of birthplace leaves the chemical fingerprints we're seeing now? The proportions of gases streaming off 3i Atlas suggest it was assembled in a very cold neighbourhood, where carbon-bearing ices could pack into the mix as generously as, or even more than, water. That points to regions beyond the familiar snowlines we think about in our own system, the places where different ingredients freeze out as you move away from a star. Imagine shelves in a pantry arranged by temperature. Closest to the star, only the most stubborn refractories survive. Farther out, water locks in. Beyond that, carbon dioxide and other volatiles join the recipe. 3i Atlas looks like a loaf baked from the outer shelves of that pantry. It also may carry the imprint of time. Ages of radiation can make surfaces darker and more carbon-rich, so what we see today could be a blend of our ancient formation and slow surface cooking during a very long journey. Could it be older than our Sun? Possibly. The galaxy is home to multiple stellar populations, some metal-poor and ancient, some younger and richer in heavy elements. If 3i Atlas formed around a star born early in the Milky Way's history, its interior would record a different cosmic kitchen, fewer metals to build with, different dust-to-ice ratios, perhaps a stronger tilt toward carbon-heavy ices in the deep cold. On the other hand, a younger system with a bustling set of giant planets could just as easily have ejected a comet with a similar outer disk signature. Age, chemistry, and ejection history are tangled together. They don't hand us a neat label. What they do give us is a set of clues we can weigh against each other. The gases we detect now, the way activity turns on and fades, the texture of the dust, each clue nudging us toward a more likely origin story. People naturally ask, can we trace it back to a specific star? With present tools, that's like trying to identify a leaf's tree after it's been through 100 rapids. We can integrate the path backward through space and compare it to the motions of nearby stars. But tiny uncertainties explode over millions of years. A gentle nudge from a cloud, a whisper of drag from the interstellar medium, and the breadcrumb trail scatters. Even so, the exercise isn't wasted. Working backward helps narrow the neighbourhoods it might have come from, whether its speed and direction fit best with stars that share the Sun's broad galactic stream, or with the thicker, older component of the Milky Way, where orbits are puffed up and more chaotic. If 3i Atlas turns out to move like a citizen of that older crowd, then the ancient origins picture gets a little brighter. There's a humbling backdrop to all this. Interstellar comets are probably not rare. Planet building is wasteful. As giant planets grow, they fling staggering numbers of small bodies outward. Most are swallowed by their sun or shattered in collisions, but a great many escape. Over the lifetime of the galaxy, every star has contributed to a loose, invisible population of wanderers. We seldom notice them because they are tiny, dark, and fast. They don't glow unless sunlight warms their skin in just the right way, and we happen to be looking. The last decade taught us that when our surveys get sensitive enough, these visitors appear. They slip in on hyperbolic arcs, put on a modest show, and then disappear into the silence again. If we think of 3i Atlas as a message, what does it say? First, that the outer zones of other planetary systems are rich and varied, not carbon copies of our own. Second, that the processes which clear those zones, planetary migration, gravitational billiards, distant stellar flybys, regularly seed the galaxy with messengers we can read. Third, that time is a powerful sculptor. The longer a comet wanders between the stars, the stranger its outer skin becomes, and the more it can fool us about what lies beneath. To hear that message clearly, we have to listen across many wavelengths and compare what we find with the best models of comet formation and aging. The deeper promise is philosophical as much as scientific. Every interstellar object is a core sample of somewhere else. We can't yet send spacecraft to every newborn system simmering in the galaxy's arms, but sometimes a fragment from one of those systems drifts to us for a brief visit, carrying the smell of its home kitchen in the ices and dust it sheds. 3i Atlas may have been baked in a colder oven, marinated in radiation for longer, and ejected by a wilder set of planets than anything we've experienced here. Or it may surprise us and point to a more familiar kind of birthplace, with a few crucial differences we haven't considered. Either way, it deepens the picture of how worlds form by reminding us of something easy to forget. Our solar system is one example, not the template. And so, Ancient Origins isn't a final verdict, but a working map. A young star's cold outskirts, a shove from a giant planet or a companion sun, a slow crossing of interstellar distances where time hardens the skin and preserves the core, then by chance a pass through our neighbourhood, long enough for us to read the outermost lines of its story before it turns the page and leaves. 3i Atlas doesn't resolve the mystery of where it came from. It makes the mystery richer, sharper, more beautifully specific, and it reminds us that the galaxy is full of places where stories like this begin. The most beautiful part of this story is how many sets of eyes are watching at once. When a messenger like 3i Atlas sweeps in, the whole observatory ecosystem, from backyard telescopes to billion-dollar spacecraft, spins into a kind of orchestra. Each instrument has a role. Some catch the big picture, some zoom in on chemistry, some watch from angles Earth can't reach, and some keep time by revisiting the same target night after night to measure how quickly it changes. Start with the watchful sentries in space. The Hubble Space Telescope didn't just take a pretty picture, it set crucial limits that ground everything else. By separating the glare of the dust from the unresolved heart, Hubble boxed in the nucleus to a modest comet middleweight and revealed a compact teardrop-shaped glow that tells us activity is real and sunward biased. Those streaked star trails in the background, that's Hubble tracking a fast, unbound traveller, proof in the image that this object is not moving like our local comets. From a single frame, you get physics, speed, direction, and a coma that isn't symmetrical. Then there's the James Webb Space Telescope, which listens for heat and fingerprints of molecules rather than looking for sharp shapes. Webb's early spectra delivered the headline surprise: a coma dominated by carbon dioxide, with water, carbon monoxide, carbonyl sulfide, dust, and even signs of water ice mixed in. That gas mix is a Rosetta Stone for the comet's past, pointing to either a very cold birth environment or layers processed by long exposure to radiation, or both. In practical terms, it tells every other observer where to look. If carbon dioxide is driving the show, then early activity, jet geometry, and dust behaviour will all follow different rules than a water-dominated comet. Ultraviolet eyes add a different layer to the portrait. NASA's Swift Observatory caught the unmistakable UV signature of water breaking apart, hydroxyl, while 3i Atlas was still far from the Sun by ordinary comet standards. That's a big deal for timing. It means water is awake earlier than expected. Pair that with Webb's carbon dioxide bombshell, and you get a nuanced picture. Carbon dioxide may be opening the vents and lofting fine ice grains off the surface, while water joins the outflow sooner than our rulebook predicted. Watching those two signals rise and fall together over weeks is how scientists test whether the early activity is superficial frost, deeper plumbing, or a patchwork of both. Of course, Earth isn't the only vantage point. As 3i Atlas skimmed past the orbit of Mars, the European Trace Gas Orbiter managed a faint moving detection from the red planet's neighbourhood, likely the closest view anyone will get. It's not about dramatic images, it's about geometry. Seeing the comet from a second platform gives a subtly different angle on the coma and background, helping disentangle what's intrinsic to the comet from what's just perspective. Add Mars-based attempts by other instruments, and you begin to see why planetary missions are folded into these campaigns. They extend our reach and give us parallax on a visitor we'll never chase with a dedicated probe. Back at home, the ground network does the patient, unglamorous work. Wide-field surveys that first flag the object keep watch for changes in brightness and morphology. Mid-size and large telescopes, think 8 to 10 metre class mirrors, hand off to spectrographs that tease out faint gas lines and dust properties. Because Earth's atmosphere hides or muddles some infrared bands, observers use clever strategies. They track proxy lines that leak through our sky, watch for telltale features in the near-infrared and visible, and combine those with polarimetry to infer the size and texture of dust grains. One team might sit on the object for hours to capture a night-long light curve. Another might return every few nights to watch how the coma grows and the tail pivots as the geometry changes. In aggregate, these measurements become a time-lapse of the comet's breathing. Solar observatories join for the hottest act. Around the tight swing by the Sun, coronagraphs designed to block solar glare can sometimes snag comets as ghostly needles of light. Even a handful of frames taken near closest approach can show whether the dust production spiked, whether jets rotated, or whether the tail briefly sharpened into a spike pointing sunward, an anti-tail caused by our changing line of sight through the sheet of dust along the comet's orbit. If that happens, ground-based observatories on the far side of the glare window will know to look for lingering dust features when the comet reappears. The choreography across these platforms isn't accidental, it's scheduled like a relay. Before the swing around the Sun, infrared and UV teams gather before baselines, which gases are present, how the dust scatters light, how fast the coma expands. During the turn, solar-facing instruments get their brief window. Afterward, when 3i Atlas emerges into the dawn sky for Earth's observers, the baton passes back to Hubble, Webb, if geometry allows, and the ground network to capture the after phase. Which volatiles linger, how quickly the coma collapses, whether the colour of the dust shifts as fresh material is spent. String those phases together and you've essentially watched a miniature climate cycle play out on a world smaller than a city. Citizen scientists and skilled amateurs plug real holes in that schedule. Big telescopes can't babysit a comet every clear night, but a network of smaller instruments can. When professionals call for nightly snapshots to monitor a suspected jet or to catch an outburst, amateurs deliver, especially in the tricky, low-altitude windows near dawn. Their images, calibrated and time-stamped, are often the earliest flags that something changed. More than once, those alerts have triggered rapid response observations with larger facilities before a fleeting feature faded. Data discipline matters as much as aperture. All of these images and spectra flow into public archives, where teams that didn't take them can still analyse, cross-calibrate, and argue with the conclusions. That's how unusual claims survive scrutiny. If one group measures a carbon dioxide surge, another can pull independent data from the same night and check whether their instrument saw it too. If someone reports water turning on early, others can revisit UV data to confirm. For a one-time visitor like 3i Atlas, that redundancy is insurance. There is no, we'll try again next apparition. What's everyone hunting next? First, evolution. If carbon dioxide keeps dominating even as the comet swings inward and then heads out, that points to a deep, intrinsic reservoir, and perhaps a formation zone laced with carbon-rich ices. If water starts to catch up and the mix shifts, layering becomes the favoured story, an outer skin rich in carbon dioxide giving way to deeper, water-heavier strata. Second, geometry. As the viewing angle changes in December and into early 2026, expect careful measurements of the tail structure, the coma's shape, and any rotating jets. Those patterns betray the spin state of the nucleus and the location of active patches. Third, isotopes. With luck and enough signal, teams will probe ratios of rare isotopes in carbon or oxygen, subtle fingerprints that hint at the chemistry of the star system, where this wanderer was born. There's also a procedural victory here that will outlast the comet. The campaign around 3i Atlas is stress testing our rapid response playbook. Survey pipelines that once looked mainly for near-Earth asteroids are now tuned to flag interstellar speeds and angles. Space telescopes are demonstrating that they can pivot quickly to capture early chemistry, and then return after the glare window. Planetary orbiters are proving they can reach past their home worlds and contribute to sky science when geometry offers a gift. The next time an interstellar traveller appears, this machine will spin up faster, ask sharper questions, and waste less precious time. And that's really the point of all these eyes, not just to admire a rare visitor, but to practice reading the universe when it sends us a postcard from somewhere we cannot go. 3i Atlas is a moving lesson in coordination. It shows how an observatory on a mountaintop, another beyond the atmosphere, and a spacecraft orbiting a different planet can each hold a piece of the same puzzle. Put the pieces together, and you don't just explain one comet, you widen the map of what's possible when worlds are born under other suns. Let's be honest about the question everyone secretly wants answered. If a visitor like this ever lined up with our planet, what then? 3i Atlas is harmless, but it's also a dress rehearsal. It teaches us how to tell a false alarm from a real one, how fast our warning systems wake up, and what buttons the world would push if interesting ever turned into incoming. The first line of defence is simply seeing the thing early enough to matter. Wide-field surveys sweep the sky each night and hand suspicious dots to rapid response software that estimates a rough path within minutes. That first pass is a sketch, not a verdict. Over the next hours to days, telescopes across longitudes take fresh measurements, shrinking the uncertainty until the path snaps into focus. For slow, local asteroids, that tightening can happen over weeks. For a hyperfast interstellar object, it has to happen much faster. In practice, the World's Watch centres run two parallel checklists: what is it, and where is it really going? A fuzzy coma means you're dealing with a comet, which can be nudged by its own jets, a star-like point with no haze leans asteroid. Both can be harmless. Both can be trouble. The key is cadence. Get as many precise observations as possible, as quickly as possible. Trajectories aren't just lines on a map. They're living things that get crisper as you feed them data. With each new night, the cloud of possible futures shrinks. Sometimes the risk probability briefly rises before it falls, an unnerving but normal part of the process as the model stops guessing and starts knowing. If the candidate comes close enough, planetary radar can ping it and return a shape and spin state, which collapses the uncertainty even further. But if the visitor is truly interstellar, the window for radar may be tiny or non-existent. That's why photometry and spectroscopy matter so much. The way brightness wiggles can reveal a tumble, and the gas mix hints at how strongly jets might shove it sideways. Those details change the aim point, by a little if you're lucky, by a lot if you're not. If the path stays cleanly away from us, the story ends with science and a sigh of relief. If it narrows toward our world, the playbook splits into two branches: space solutions and ground solutions. Space solutions are about changing the rock's path. Ground solutions are about getting people out of the way. Space solutions start with the gentlest nudge, hit the object hard and early so a tiny change today becomes a huge miss later. That's the logic behind kinetic impactors. We've already demonstrated this on a small asteroid in deep space and watched its motion change. Proof that momentum transfer works in the real world, not just on whiteboards. The catch is lead time. To move something big by a safe Earth radius distance, you want years, not weeks. If discovery comes late, you can stack the deck with multiple impactors arriving in quick succession, or target the surface in ways that throw extra material outward to enhance the push. You can also imagine a constellation of smaller interceptors that swarm in, each adding a tiny tap that adds up to a life-saving shove. When time is generous, think many years to decades, slow force options come into play. A gravity tractor is literally a heavy spacecraft that flies in formation near the object, letting mutual gravity tug the target onto a slightly new course. It's elegant and controllable, but it demands patience and precise navigation. Variants of the idea use ion beams or gentle ablation to produce a sustained, directed thrust without ever touching the surface. These are surgeons' tools, not emergency room trauma kits. At the far end of the spectrum is the last resort option, a high-energy standoff that flashes the surface into vapor and hot ejector, kicking the object the other way. The goal here isn't to shatter the body into 1,000 bullets, it's to puff the surface and let the plume act like a rocket exhaust. This concept has been studied for decades and remains the only tool with enough raw muscle to budge something large on short notice. But it comes with heavy political, legal and coordination baggage, and would only be considered if nothing else could work in time. Comets complicate everything. A rocky asteroid is often a stubborn, mostly predictable mass. An active comet can be a cluster of weakly glued blocks surrounded by vents and jets that change with sunlight. Push too hard, and you might fragment it. Push at the wrong spot, and the jets may do the rest of the steering for you in directions you didn't plan. That's why a reconnaissance flyby, minutes to hours before an impact, can be invaluable, giving controllers one last look at the surface to pick a safer aim point. With short warnings, that flyby camera might sit right on the impactor itself, relaying images until the final seconds. Now for the ground branch, the part that protects people when space solutions aren't possible or aren't needed. If the object is small, the right answer is civil defense, not rockets. Predictive models can outline a corridor on the map where debris or an airburst is likely. With even a few hours warning, that corridor can be cleared of aircraft, trains rerouted, and first responders pre-positioned. With days, you can move people out of harm's way, protect key infrastructure, and stage recovery resources. Emergency managers already trained for fast-moving, low-probability, high-consequence events. A Skyfall alert plugs into those same muscles. The difference is the lead time. Meteorology gives you forecasts in days. Planetary defense might give you hours to weeks. Clear communication makes the difference between orderly action and chaos. Expect briefings to start cautious and conservative, no impact expected, and only escalate if the numbers demand it. Public messaging is a tool of its own. You'll hear probabilities, not prophecies. You'll see language like 1 in 1,000 a day, trending down as the fit improves. That isn't hedging, it's transparency. The worst outcome isn't an object that safely misses, it's panic created by rumour. The systems built around these events emphasise one voice per region, regular updates, and simple, consistent graphics. Where the object is, where it could go, what officials want you to do, and when the next update arrives. Where does a visitor like 3i Atlas fit into all this? It's a low-stakes teacher with high-value lessons. Its hyper-fast, unbound path forces orbit solvers to deal with the same math they'd face in a riskier case, including subtle nudges from outgassing. Its early, unusual chemistry pushes observers to diversify the wavelengths and cadence they use. Exactly the habits you want when time is tight, and the object is odd. Its safe miss distance gives radar teams and survey pipelines a live-fire drill without any of the sirens. And its months-long arc through the inner system lets analysts test how well different models predict motion between observing gaps, which is crucial if the next interstellar visitor blazes in on a tougher trajectory. Zooming out, the strategic picture is getting stronger every year. More eyes are coming online in the next few seasons, scanning deeper and faster. Space-based infrared observatories designed to spot dark, warm objects will fill the blind spots that ground telescopes struggle with. Data pipelines are learning to flag weird movers that don't behave like bound solar system bodies, exactly the signature of an interstellar interloper. On the response side, mission teams are treating deflection not as a science project but as a capability. Standardized impactor buses, playbooks for rapid launch, and international frameworks for decision-making that can move at the speed of the problem. Here's the sober bottom line. A direct hit from a large interstellar object is extremely unlikely in any given year. But unlikely isn't impossible, and our job isn't to be lucky, it's to be ready. Readiness means finding threats early, modelling them honestly, deciding quickly, and choosing the simplest tool that works with the time you have. Most days that tool is a press release that says, no risk. On a harder day, it might be a rescue of a narrow corridor on the ground. On the hardest day, it could be a spacecraft sprinting out for a one-time nudge that separates our line from theirs. 3i Atlas reminds us that the universe doesn't owe us easy problems. It also shows that we're building the muscles to handle harder ones. Better surveys, faster coordination, clearer communication, and real hardware that can change the outcome. If a future visitor ever lines up with Earth, our best protection will be everything we learned from the harmless ones that came before. Why does this brief, dim traveller matter so much? Because every time a fragment from another star system drifts through our sky, it gives us a real, tangible sample of someplace we can't visit. 3i Atlas is not a theory or a simulation. It's a piece of a distant planetary kitchen shedding dust and gas right in front of our instruments. That makes it a decoder ring for questions we usually answer by inference. How other solar systems store their ices, which ingredients get locked away in the cold, and how sunlight, time and radiation sculpt small worlds in deep space. Even without scooping a single grain, we can read its chemistry in the light it reflects and emits, and that chemistry widens the map of what normal looks like beyond our sun. 3i Atlas also solves a statistical problem in the quietest possible way. it's another data point. With only 1 or 2 interstellar visitors, it's hard to know whether you've met the typical neighbour or the neighbourhood weirdo. Add a third and patterns start to appear. You begin to see a spread in behaviour and composition, rather than a single story, which hints that distant planetary systems don't all bake their comets from the same recipe. If you care about how planets form, and by extension, how often worlds like ours might appear, this matters. It's like moving from a single snapshot to a tiny flip book. The picture isn't complete, but it's finally in motion. Then there's the physics 3i Atlas pokes at. Comets are supposed to wake up as they warm, but which ices wake first, how fast they vent, and how dust responds are details we still wrestle with. Watching a truly foreign comet evolve day by day forces us to test our models under conditions we don't control. If something turns on earlier than expected, or a certain gas keeps dominating when it shouldn't, that's a gentle but firm note from the universe that our assumptions need tuning. Those corrections don't just apply to this one visitor, they ripple through how we interpret every faint, distant comet we observe later, local or interstellar. 3i Atlas strengthens the way we do science together too. A one-time, fast-moving target is a stress test for coordination. Survey telescopes must flag it quickly. Follow-up teams have to pivot across continents. Space observatories need to carve out time on short notice. Analysts stitch the results into a coherent timeline. Each smooth handoff becomes part of a playbook that will be priceless when the next interstellar object appears. The more we practice on a harmless visitor, the less we'll fumble when something stranger, dimmer, or faster shows up. That readiness isn't just about pride, it's how you turn a fleeting opportunity into enduring knowledge. The benefits spill well beyond comet lore. Planetary defense groups get a live drill on tracking an object with unusual motion and subtle, non-gravitational nudges. Exoplanet researchers gain constraints on the raw materials swirling in other systems, backing up what their giant telescopes infer from disks around young stars. Heliophysicists, people who study the sun's influence, watch how solar light and wind reshape a fragile coma in real time. Even meteor scientists watch for dust dynamics that might someday seed faint meteor streams. One visitor, many classrooms. There's a creative spark here for engineering as well. Mission designers sketch faster interceptors, smarter autonomy, and standby probes that can wait in deep space and pounce when a worthy target appears. Data teams refine the pipelines that spot odd movers on the sky, so that interstellar candidates rise to the top in hours instead of days. And instrument builders think about the next generation of sensors that can pry more detail from something small, dark, and racing away. Progress comes in quiet increments. A better scheduler, a more sensitive detector, a sequence of observations we didn't prioritize before. Add them up, and the next encounter turns from barely manageable into richly characterized. Astrobiology sneaks in at the edges too. No, 3i Atlas isn't carrying messages in bottles, but when you measure the ices and dust, you're sampling the inventory of another system, the solvents, the carbon carriers, the grains that can host simple chemistry. If the proportions feel familiar, that whispers that life's raw materials might be commonplace. If they feel alien, that tells us just as much. Some kitchens stock different staples, and yet they still form planets and comets. Either outcome is a win for understanding how often the universe sets the table for biology. Equally important is the legacy that doesn't make headlines. Data from 3i Atlas will sit in archives for decades, ready to be reanalyzed with new techniques, compared against future visitors, and fed into ever better models. The images and spectra become a training set for algorithms that will comb tomorrow's survey torrents. The observing strategies, what worked, what didn't, which wavelengths were most revealing at which times, become institutional memory. When a graduate student in 10 years asks, how do we plan a campaign for an unfamiliar interstellar object? The answer will include pages written during these months. 3i Atlas also matters because it gives the public a clean story to hold on to. Not doom, not hype, just the simple wonder of a thing from another sun drifting past ours. That story is fuel. It powers interest in math classes and physics labs, gives context to the telescopes we build, and reminds people that the sky isn't just a backdrop, it's a place with traffic. Curiosity is a renewable resource in science. Visitors like this refill the tank. And finally, there's the quiet perspective it offers. Our solar system can be a little provincial. We know its rhythms so well that it's easy to think of them as universal. 3i Atlas is a gentle nudge to look up and remember that our way is one way. In that humility is a deeper kind of confidence, the sense that, with enough patience and coordination, we can learn from whatever the galaxy throws our way. The visit will be brief. The lessons will last. Some visitors leave with fireworks. This one leaves with questions, and somehow that's even better. As 3i Atlas fades back toward the quiet between the stars, it leaves us standing where we began, under one sky, looking up, a little less certain and a lot more curious. We didn't get a dramatic sky show or a headline-grabbing close pass. We got something rarer, a new clue about how other solar systems live and breathe, a reminder that the universe is bigger in its details than in its size. If you've stayed with me through this whole journey, thank you. We met a traveller we'll never meet again. We watched it arrive from the deep, brush past Mars's neighbourhood, slide behind the sun, and whisper back into the dawn. We learned why it's not coming to Earth, why its path is a clean flyby, and why that's actually perfect, for our nerves and for the science. We listened to the strange music in its coma, carbon dioxide louder than water, water waking earlier than expected, dust moving to rhythms we're still learning to read. We let the big observatories take their turns, the small telescopes keep the beat, and the instruments at Mars add a harmony we couldn't get from home. And somewhere in all that, we glimpsed its first home, a colder pantry, a different recipe, maybe even an older kitchen than our sun's. That's the gift of a visitor like this. It doesn't validate a theory so much as widen the room where all our theories have to sit together. It nudges us to be humbler with what we think is universal, and braver with what we're willing to ask. What if there are far more carbon-loud comets than we ever guessed? What if the ways ice wakes and dust flies are more diverse than our models allow? What if the rules we wrote from local examples are just the opening scene in a much larger play? 3i Atlas doesn't answer those questions. It points to the door and holds it open for the next traveller. And now, a moment for you. I'd love to hear what this visit stirred up. If you could ask one question of a comet from another star, what would it be? Where do you think 3i Atlas began? An ancient outer disk around a quieter sun, or a young system with rowdy giant planets kicking everything around? Did this change how you picture our own solar system? Less like the standard model, and more like one neighbourhood among many? Drop your thoughts below. I read as many comments as I can, and the best part of making these videos is the conversation that keeps going after the credits roll. If you found something here worth your time, an idea, an image, a moment of wonder, consider subscribing. It helps the channel reach more curious minds, and it tells the algorithm that the slow, careful kind of science storytelling still has a place on the internet. If you want to go deeper, share this with a friend who loves space, or with the person in your life who needs a gentle reminder that our routines are happening inside a miracle. For those who want more right now, I've put together a path for your next steps. Start with our earlier journeys into interstellar visitors and weird comets, how they form, why they change shape, and what their chemistry whispers about their birthplaces. Then, if you're in the mood to look ahead, check out our pieces on how we search for objects like this, and the tools we're building to greet the next one. Each video is a chapter in a much longer story. How a species tied to one small world learns to read messages carried by ice and dust across the emptiest distances. To the night owls and early risers watching this on their phones by a window, step outside tonight, even for a minute. You won't see 3i Atlas with the naked eye. You probably won't see anything dramatic at all, but you will stand under the same dark ocean that delivered a fragment of another sun to our doorstep, and that is worth feeling in your bones. Listen to the quiet. The sky's not empty. It's a library, and once in a while, a book falls open as it passes by. Before we go, a small promise about this channel. We don't chase panic, we chase perspective. When the news cycle flares, we take a breath and look for the deeper pattern, the detail that turns spectacle into understanding. 3i Atlas gave us a perfect chance to practice that. No doom, no hype, just a fast, fragile thing that told the truth about the galaxy by being itself. If that's the kind of story you want more of, you're in the right place. Thank you for spending your time here, for the likes, the shares, the questions, the corrections, the patience. Thank you for caring about a visitor most people never saw, and for giving it the attention it deserved. The comet is already fading, but the work it inspired, new methods, new collaborations, new young minds deciding to study the sky, that lingers. That's how these brief encounters become lasting change. Wherever you are, I hope you get a clear night soon. Tilt your head back. Somewhere out there, another wanderer is on its way, carrying another piece of a story we don't know yet. When it arrives, we'll be here together, ready to listen, ready to learn, and ready to be surprised again. Good night, and keep looking up.